Hello everyone, welcome to EnviroPioneers. In this video, we are going to learn the basics of synthetic aperture radar, that is an advanced technique within the active microwave remote sensing. Till now, in last two previous videos, we have learned that when a platform moves along a track, the radar system illuminate a particular portion on the terrain by transmitting a sequence of short microwave pulses which are characterized by their pulse length and the instantaneous area on the ground which is being illuminated is referred as the antenna footprint. The system scans the ground in two directions. One is range direction and second is the azimuth direction. And to form a two-dimensional image, the reflection received from the ground are sorted by their arrival time in both range and azimuth direction. In last video, we also discussed about the spatial resolution, that is the ability of the system to resolve the objects on the ground. And in active microwave remote sensing, this spatial resolution is given in two dimensions, the range resolution and the azimuth resolution. So the range resolution is calculated for the range direction, that is across track direction, or we can say it is perpendicular to the flight direction. Range resolution depends on the pulse length, and the objects at different ranges can be distinguished if their separation is larger than half the transmitted pulse length. And second is the azimuth direction, that is along track or parallel to the flight direction, and it is defined by width of the antenna footprint in the azimuth. In azimuth resolution, the angular beam width is directly proportional to the wavelength of the transmitted pulse and inversely proportional to the length of antenna. It means the shorter the wavelength or longer the radar antenna, the narrower is the beam width and higher is the azimuth resolution. In real aperture radar, the azimuth resolution is calculated by this formula where we have the slant range distance into wavelength divided by the length of antenna. Suppose if a side-looking airborne radar is using a particular wavelength to operate. In that case, here two parameters are fixed, wavelength as well as length of the antenna. So the azimuth resolution depends mainly on the slant range distance, which indicates that the azimuth resolution varies from near range to far range as the distance increases. And as we saw through example in the last video, that this azimuth resolution it degrades linearly with increasing distance between the sensor and the ground. And due to dependence of the azimuth resolution on the distance to the ground, it makes the application of side-looking airborne radar highly impractical on high-altitude platform or spaceborne platform. It can be understood through this example. Suppose if there is side-looking airborne radar system operating at wavelength 0.03 meter and it is utilizing an antenna having the length of 3 meter. Now we have two conditions. In first condition, it is assumed that this system is operated from an aircraft flying at the height of 3000 meter and it is observing the terrain at the depression angle of 30 degree. So we can calculate the azimuth resolution for the system using this formula which we discussed in the last video where we saw that azimuth resolution can be calculated using the height of the platform, depression angle, wavelength and the length of antenna. So for this case, the height of the platform is 3000 meter, depression angle is 30 degree, wavelength is 0.03 meter and length of antenna is 3 meter. So when we calculate putting all the values in this equation, we get the azimuth resolution of 60 meter. Now the second condition is if the same system is operated from a spaceborne platform at the height of 800 kilometer, then if we calculate using this same formula where height is 800 kilometer and all the values are nearly same, so when we calculate the azimuth resolution is 16 kilometer. So we can see because of the dependency on the distance to ground, the azimuth resolution decreases as the height of the platform increases. As azimuth resolution is inversely proportional to length of antenna, great improvement in azimuth resolution can be achieved if a longer antenna were used. But due to practical limit, the maximum length of antenna that can be used in the case of real aperture radar is 2 meter. So a major advancement in radar remote sensing has been the improvement in azimuth resolution through the development of synthetic aperture radar system. Engineers have developed procedures to synthesize a very long antenna electronically. The aperture synthesis principle allows to create, or we can say to synthesize, a much longer effective antenna that is referred as the synthetic aperture, and this is synthesized from a sequence of acquisitions made with a short antenna as it moves along its flight line. Now let us understand the concept of synthetic aperture radar. In this terminology, aperture means antenna size and synthetic aperture means a virtual antenna. So in the synthetic aperture radar, as the platform moves forward, the system transmits many radar pulses towards the terrain. Each pulse reflects from a slightly different position on the ground. This system receives the backscattered signal, and these signals are combined through signal processing algorithm to create a very large antenna. So synthetic aperture means artificially creating a large antenna using the motion of the platform. Like real aperture radar, a synthetic aperture radar also uses a relatively small antenna on the platform. Now, depending upon the speed at which this platform is moving, we can say that this radar antenna is moving at a velocity v along its flight path. And as it is moving, it is continuously sending thousands of pulses towards the terrain. So, the time gap between each pulse is defined by the pulse repetition time. That is the time interval between two successive radar pulses transmitted by the synthetic aperture radar system. And this pulse repetition time is inversely proportional to pulse repetition frequency. So here it is mentioned that PRT, that is pulse repetition time, it is given in microsecond or millisecond, and it represents the time gap between the pulses. And this PRF, that is the pulse repetition frequency, it is given in hertz, and it represents how many pulses are transmitted per second. So shorter the pulse repetition time, it means high pulse repetition frequency, means the system transmits more pulses and it gives better data acquisition for SAR processing. In synthetic aperture radar, Doppler principle is used to monitor the returns from all these pulses to synthesize the azimuth resolution. The Doppler principle states that the frequency of sound changes if the listener and or source are in motion relative to one another. Suppose if we are standing on a railway station and a train is approaching towards us, so the siren or the whistle will have an increasingly higher frequency pitch as it approaches. This pitch will be highest when the source is directly perpendicular to us and it is referred as the point of zero Doppler. And as the train passes by, its pitch will decrease in the frequency in proportional to the distance we are from the source. Here also, the Doppler effect is explained. In the case of the stationary sound source, the observer will receive the constant frequency. But as the source is moving towards the observer, frequency increases, and as the source is moving away from the observer, frequency decreases. And this Doppler principle is applicable to all harmonic wave motion, including the microwaves used in the radar systems. So, in the synthetic aperture radar, a long antenna can be synthesized using a short antenna by taking the advantage of the aircraft's motion and the Doppler principle. And during the data acquisition in synthetic aperture radar system, these assumptions are made that the terrain is stable and not moving, and the object of interest remains a fixed distance away from the aircraft's flight line. As the synthetic aperture radar system is moving along with the platform, this system is constantly transmitting short radar pulses towards the terrain, and it receives the echoes returned from the objects on the ground. Let us understand the synthetic aperture radar through two examples. Here we have the first example. When system moves along the flight path, this object on the ground is illuminated by several antenna position. So as the sensor moves, point x1 is the first time the system receives the backscatter signal from the object P, and it will continue to receive the signal as it moves along the flight path. And x2 is the last time the system receives the backscatter signal from this object. So here it is mentioned point x1 is the first time object P is seen, and point x2 is the last time P is observed. So this object P on the Earth surface, it is imaged by many consecutive radar pulses as the system moves along the flight line. Now, in the second example, this ship is considered as the target, and as the aircraft is flying in this direction, it is azimuth direction. So, as the aircraft reaches to the position A, it is the first point where this target enters into the radar beam. The system will receive and record backscattered echoes from this target for each of the transmitted pulse. And as the platform continues to move forward, all echoes from the target for each pulse are recorded during the entire time that the target is within the beam. So, in this example, A is the first point where this target was observed, and D is the last point where the observation related to this target was made. So, in both the examples, the target or the ground point remains in the beam for some duration, and during this duration, the radar collects many echoes from that target. So each echo is received from a slightly different position. It means the ground point or the target is observed from multiple angles. It is observed at multiple times and with multiple phase measurement. And the processor in the system stores all backscattered signals for each of the transmitted pulse as amplitudes and phases for the time period t, and this t is the time taken by antenna to move from x1 to x2 in the first example and from A to D in the second example. Once the data is acquired, post-processing approach is applied to combine all acquisitions into a single data set that looks like as it was acquired with a much longer antenna. By coherently adding these radar returns, the system constructs a virtual antenna length. And as we know, speed is equal to distance by time. So we can calculate distance, that is the synthetic length, using this formula where v is the speed of platform and that is known, and t is the time the target stays in the radar beam. So this synthetic antenna is much longer than the real antenna. So, this longer or the virtual antenna is typically known as the synthetic aperture, as it is synthesized from a number of acquisitions made with a shorter antenna placed on the platform, and the motion of the antenna along the azimuthal direction is utilized to synthesize or to give the effect of a long antenna. If you note, here we use one term coherently, and at some of the places you will find this definition for synthetic aperture radar, that it is a coherent, mostly airborne or space-borne side-looking radar system which utilizes the flight path of the platform to simulate an extremely large antenna or aperture electronically, and that generates the high resolution remote sensing imagery. So, in the radar system, coherence refers to the stable phase relationship between the transmitted and received electromagnetic pulses. In this image, we have the simple representation of coherence. This is the stable continuous oscillation as reference. Here we have the phase of the transmitted signal and phase of the received signal for each of the pulse. And here we can see the phase of the received signal is same as the phase of the transmitted signal. But in rest 3 cases, we are having the random phase. So a coherent radar system preserves phase information which allows the precise measurements of the target through the techniques like the Doppler filtering. In synthetic aperture radar, the azimuth resolution is given by L by 2, where L is the virtual length of the antenna. If you remember, in real aperture radar, this azimuth resolution was dependent on the height of the platform, depression angle, the wavelength used, and the antenna length. But in synthetic aperture radar, the azimuth resolution is independent of range distance or the sensor altitude. During the data acquisition in synthetic aperture radar, problem of speckle occurs, and this is referred as the noise in data collection. So this speckle is a grainy salt and pepper pattern in the radar imagery, which is formed due to the coherent nature of the radar wave, which causes random constructive and destructive interference. In this image, these are the pixels which represent the illuminated area, and this is the SAR image generated from the data acquisition. We can see some of the pixels because of the constructive interference are brighter, while some of the pixels because of the destructive interference are darker. So these random bright and dark areas in the radar image gives it grainy salt and paper pattern, which is referred as the speckle. And this speckle can be reduced by processing separate portions of an aperture and recombining these portions so that interference does not occur. As the coherent nature of the synthetic aperture radar signal produces the speckle in the image, to remove the speckle, the image is usually processed using several looks, means observing the terrain from different look direction, and then an averaging takes place. So in case of a speckle, if this process is done, the equation for azimuth resolution is adjusted by multiplying the number of looks into the formula. This adjustment we can understand from this example. If SAR had a 12-meter antenna, so the azimuth resolution will be 12 divided by 2, so it will be 6 meter. But if the speckle in SAR data were processed using 4 look to improve the interpretability of the data, so in that case, the adjusted azimuth resolution will be 4 into 12 divided by 2. So it will be 24 meter. Now coming to the topic radar interferometry. So the SAR data enable an analysis method called interferometry. So interferometry is a measurement technique that uses the interference of superimposed waves such as light waves, radio waves or sound waves to extract the information about the waves or the materials they interact with. So when this interferometry is used with the SAR, this analysis method is called Interferometric SAR or InSAR, and this InSAR uses the phase information recorded by the instrument to measure the distance from the instrument to the target. And by acquiring the multiple SAR image of the terrain, it can be used to extract three-dimensional or velocity information. So the imaging radar interferometry is the process where radar images of the same location on the ground are recorded by the antennas at different locations or at different times. Imaging radar interferometry can be used for interferometric topographic mapping or interferometric velocity mapping. So, this interferometric topographic mapping is based on acquiring the data from two different look angles. And here we assume that scene which we are imaging, it did not move between the data acquisition. And these two measurements can be done from two radar placed on the same platform separated by few meters, and it is referred as the single pass interferometry, or it can also be conducted using a single radar that obtains two measurements on different orbital track that are closely spaced but a day or so apart. Means here the flight direction of the aircraft is changed and the data is acquired at the interval of few days, and this is referred as multiple pass or repeat pass interferometry. In interferometric velocity mapping, the look angles of multiple data acquisitions are held constant, and if there is no sensitivity of topography, then this interferometry can be used to extract the information about the things that have changed in the scene. Using the interferometric velocity mapping, quantitative information about the velocity of the objects that moved between the two observations can be made, and this has the application in measuring the movements along the fault lines, seismic displacement due to the earthquake, mapping the glacier velocity, or monitoring the ocean currents. So this was all for the synthetic aperture radar. In the next video, we will learn about the factors affecting the backscatter signal and the application of active microwave remote sensing. These are the references. First one is the reference of the book Remote Sensing of the Environment by Jensen, and these are some websites where you can get the information about the synthetic aperture radar. We will meet soon in the next video. Thank you and best wishes.